But keep in mind, as we mentioned before, that with an increase, you also affect, that's why we always need to play with the balance between the two. You always want to achieve a balance between high resolution and optimal sensitivity. Why? Because the goal for you is high resolution and optimal sensitivity. For example, in the case of myocardial imaging, if you collect counts, for instance, if the counts are low, like 1 million counts, and you increase it to 4 million or even 16 million, you will see what happens to your image. The difference is very clear. Between this image and that image, the noise has decreased. Once the noise decreases, you start to see better. What is the result? The result is that what is present. But you will find that it will increase, so you don't get confused. If you go back to this lecture, you will find me explaining this part in detail, especially the difference between acoustic noise and noise. Now, regarding the topic of noise, if you want to calculate something, like the نسبة الإشارة إلى الضوضاء, this falls under what they call the image quality matrices or image quality parameters, something like the نسبة التباين إلى الضوضاء, something like that. All right, what is something like that? The signal to noise ratio and something like the normal contrast. This contrast is considered. For example, in any paper you read, you will find that it says, I want to perform the quantitative measurements and the qualitative measurements. The qualitative measurements involve subjective analysis, such as the scoring that the doctor gives, saying whether this image is fair or what its quality is like. The quantitative analysis always works on these parameters, which are the نسبة الإشارة إلى الضوضاء, the نسبة التباين إلى الضوضاء, and something called noise contrast. So these parameters, I don't know what it is. It's something called, what about these programs? They are all considered quantitative parameters, which may not concern you much, but the noise aspect is quite significant. However, each one has its own specific use and applications under certain conditions for the image. For example, the نسبة الإشارة إلى الضوضاء is used in specific cases if you want to see a lesion in a certain shape or location, while the نسبة التباين إلى الضوضاء can be used with low contrast detectability lesions. Each one has its own specific use, but the details may not be very relevant to you. Just understand that the noise or relative noise that we talked about and the نسبة الإشارة إلى الضوضاء, of course, reflects the image quality. It is a ratio between two things, the mean counts present and the noise. The higher the value of SNR, the less noise is present in the image, and the smoother the image becomes. If the SNR is high above a certain threshold, you will notice how the resolution starts to change and how the contrast begins to change. For example, if you look at MR images, you will find that in MRI, the SNR is provided along with the acquisition parameters, telling you, for instance, that you want an SNR of 1 or SNR of 1.5. If this SNR is high above a certain level, you will find that the image becomes very smooth and the details start to disappear, resulting in a very smooth image with reduced resolution. Okay, the setting of the special resolution is also important because you will read this information in something called point spread function, line spread function, and modulation transfer function. If I have a point source like this, we talked about the point source last time. This point source is taking a material of feelings. If I have this point source and it exists as a point source, then if I take a line profile for it, I am doing something called the line spread function. The curve I created represents the counts per pixel on my line, and I call this the line spread function. I call this indeed my line spread function. The modulation transfer function is considered a transformation of the line spray function, which gives you this shape that represents the relationship between the line spray in centimeters and the output. So why are you telling us this? Because the curves from the line spray function and the modulation transfer function are what determine the resolution of your imaging modality and the resolution for any lesion or point present in your image. For example, if you have a point source like this and you are imaging it, the area at the center where the point source is should have the highest activity for you, right? That's why it takes this peak. But if I move to the right side or left side, why does your curve not appear like this? Why does this curve not appear like this for me? And then it goes like this. And then like that. I'm saying point source, or why didn't it appear like that? Why didn't it appear sharply like this? Here's the legend, and here's the line profile. Sorry, at this point, this is the point where my count is. After that, I moved inside the legend. So I'm moving in this within the count. Come on. Then it drops. And they say, yes, but this talk is if you're discussing something very ideal and very theoretical, meaning something theoretical at this time. But in reality, in the real case, the curve will never come out like this. The curve must come out in this Gaussian shape. Why? Because simply, you will never be able to prevent the incoming angle 100%. You can't stop it 100%. There will always be scattered light coming at an angle. And this scattering will shape your curve like this. But what can your system see of this object? Clearly, the margin here is about the play or the friction occurring at this region. Instead of being sharp, it has become broader. So, how do I define this area or this story? I do it using the line spray function that I create with the line profile. Now, the width, which is the full width at half maximum, determines your resolution. Look at where the peak is, take 50% of my peak, see the value, and calculate x2, x1 over the value in the middle to get the full width at half maximum. The smaller its value, the higher your resolution. The larger its value, the lower your resolution. As we discussed last time, there are two types of resolution: intrinsic resolution and extrinsic resolution. If you remember the topic of intrinsic resolution, am I using kilometers or not? Okay, if I'm talking about extrinsic, then I'm using the collimator. So when I say I want to calculate the resolution of the system, I calculate the resolution of the intrinsic plus the resolution of the extrinsic, which is the collimator for the crystal. We talked about the crystal itself, and we said last time that if its thickness increases, sensitivity increases, but resolution decreases. If the thickness is low, then sensitivity decreases, but resolution increases. Got it? Well, if you are dealing with higher gamma photon energy, this will lead to the scintillation photons that are produced being high as well. This will also improve your special resolution because it will reduce the noise present. Additionally, you have the light photons that are emitted in the scintillation crystal, which go to the photomultiplier tube. There is something called a light guide. A light guide is like a channel through which these light photons travel to reach the photomultiplier tube. If, for example, your crystal is covered by a small number of light guides, then your chance of collecting more photons resulting from the interaction of the gamma photon with the crystal will decrease. The resolution will also decrease because the resolution depends on determining the location of the scintillation. It will decrease as well. It was mentioned that if you are dealing with the photomultiplier tube, the number of these photomultiplier tubes must be... The number and shape of photomultiplier tubes vary. There are types that are circular, hexagonal, and square. The square and hexagonal shapes are better because they provide a larger area than the circular shape, thus covering a larger area on the crystal. Also, when you have a circular photomultiplier tube and another circular photomultiplier tube, the gaps between these photomultiplier tubes tend to be large. These areas can lead to a loss or reduction in the efficiency of the detection of the photomultiplier tube, unlike when you have a square shape. The hexagonal gaps that are present are few, which consequently makes the detection process better for you. All right, there is also something because the motor will come to read something called energy and linearity, correction of scintillation, production. Any crystal or machine undergoes a process called calibration. The term calibration means that I am making a pre-adjustment to my machine so that it can recognize a specific signal. There is also something called quality control. Quality control tests whether my machine can recognize this signal or not. For example, I have a radiation detector. You want to measure a specific type of radiation, let's say technetium. This technetium emits 140 kiloelectron volts. So, you take this detector and perform a calibration. What does calibration mean? It means adjusting its settings. For instance, you tell it that a certain source with an energy of 140 kiloelectron volts will come, and it will produce a scintillation plate with a certain photon output. Now, you know that this energy, which the detector encountered in relation to this photon, corresponds to the 140 kiloelectron volts of technetium. This process is called calibration. So, calibration means you are making a pre-adjustment for your detectors. This term is generally used in CT, X-ray, and any imaging modality. The term calibration means you are calibrating the machine. What does calibrating the machine mean? It means adjusting its settings, making a pre-adjustment so that it can recognize the object it will detect. When I perform quality control, I take this source and place it under the machine or the source of radiation and see if the machine reads it correctly or incorrectly. This is called quality control. That's why the tests conducted on any machine are called quality control, which is performed by the medical physicist, and part of it is done by the technician who tests the efficiency of the machine to see if it reads correctly and measures efficiently or not. Now, who performs the calibration? It's the engineer. The engineer comes in if you have a result from quality control that is incorrect. At that time, he makes a readjustment to the detector saying, no, adjust it. Why am I saying this? Because there is something called energy and linearity correction that is done for the crystal, which the engineer performs. How does the engineer do this? He brings a source of radiation. This source could be technetium, or if you want to use iodine, you will use gallium, or whatever the source is. It starts by saying, I have this particular source that emits a certain energy. Then it begins to adjust something called the gain of the crystal. What does the gain of the crystal mean? My crystal has a specific field and view, and it has certain dimensions. Now, is it true that all these crystals have photomultiplier tubes on top of them? Am I currently exposing a source of radiation to the crystal? Are all the locations present, all the photomultiplier tubes, all the pixels, and all the points inside the crystal seeing this source correctly, or is there variation? If there is variation, adjustments need to be made. It should be set so that the value should come out to a certain amount. And then it starts to adjust the values between the points of the crystal that are present, making them all linear with each other. It ensures that all the photomultiplier tubes and all the crystals you have see the source as if they are a technician or whatever. If there is a difference, it will affect the intrinsic spatial resolution of the crystal itself. The special resolution, as I mentioned, is expressed as full width at half maximum. The value ranges from 0.4 to 2.5 up to 4 millimeters. This is its value, of course, depending on the crystal thickness and the type of machine. For example, you will find Siemens, GE, and Philips, which are some of the most well-known machines in gamma cameras, like Siemens. Among the specifications that are read is the value of the fall width at half maximum of the crystal. What is its value? Of course, the lower the value, the higher the resolution you achieve. The second type of resolution is the collimator we talked about. The collimator depends on the hole diameter and the distance from the radiation source to the collimator. The more the rates increase, the more the rates increase, the more the rates increase. The more the rates increase, 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 the more the rates increase. RC, which is, for clarity, why is this equation made like this? This equation is supposed to be written as I have something at the end. I have the full width at half maximum, which is a measure of the spread of a distribution, equal to d1 plus b over h, where h is the whole length. This is an important concept in physics and engineering. The longer the length of the hole, the higher your resolution should be, as you might expect, right? This means that the full width at half maximum value tends to decrease. This is because of the inverse relationship between these variables. If the distance between the collimator and the source happens to increase, your resolution will decrease, and the full width at half maximum value will increase. This is a fundamental principle in optics. The value will be in a fraction of its value. What is it? Its value. It will increase, isn't that correct? I'm sorry, this is about the hole diameter, which is the distance from the radiation source. If your hole diameter increases, your resolution will decrease, but the value of the full width at half maximum will increase. So now I have the hole diameter and the distance from the source to the collimator and the hole length. These three parameters affect the collimator's spatial resolution. As you can see here, if I have my data at a distance of 0, at distances of 5 centimeters, 10 centimeters, 15 centimeters, and 20 centimeters, let's see the line profile for each of them and how the values look. You will find here at 0, here is the line profile, and at 5 centimeters, the further you go, you will see how your line profile changes. You will notice that the width has started to increase, meaning the full width at half maximum has increased, but the resolution has decreased. You can see your margins here are clear, here a bit less, here a bit less, and here a bit less. As you move away from the collimator surface while imaging the patient, it's as if you are moving the patient away from the detector. So what will happen? You will find that your resolution has decreased, because it also said that yours will also decrease what you carry for it, which expresses kindness in a way that gently touches your heart and compassion. Here, for example, is the shape of the mediation transfer function with different distances. Here is the value of the transfer function, and the source at a 2 centimeter distance. For instance, if it were 10 centimeters, here 5 centimeters, here 25 centimeters, and 2.5 centimeters. So if we assume this is 1, this is 2, and this is 3, which one of them is the best in terms of resolution for you? 1, 2, or 3? 1. Okay. So what does 1 mean, Dr. Hani? It means that if I assume I took, for example, a value of 0.4 from the transfer function, you multiply 0.4 by 100 because it equals 40%. This means the efficiency of the machine to see or to perform detection or to achieve resolution is 40% compared to when the distance was 10 centimeters. I can see a frequency of about 0.45 centimeters at one line pair, and if the frequency is at 5 centimeters, it increases. At 2.5 centimeters, the frequency increases. What does frequency mean? It means the number of cycles per second that we talked about before, which is related to object size. The object size is linked to line pairs. The number of line pairs per centimeter indicates that the higher your frequency, the higher the number of line pairs present per centimeter. Now, if we assume you took a certain value, say 1, at 1, I want to see when the distance is 10 centimeter. That's not visible at all. Okay, when the distance is 5 centimeters, I can see it with an efficiency of 10%. When the distance is 2.5 centimeters, I can see it with an efficiency of 30%. So the distance here will affect the efficiency of the machine in seeing what? It will see a higher resolution. Now the system of special resolution as a whole, the two together, what about them as a whole? The intrinsic relationship with the collimator and the crystal together is important because when you talk about system resolution, you are considering both factors together in determining the resolution of the image. As I mentioned, a small number of photomultiplier tubes affects the low intrinsic spatial resolution, and this low threshold of photomultiplier tube voltage contributes to the signal. This is related to the idea of calibration that I was talking about earlier. Voltage contributes to the signal, which is connected to the concept I was discussing earlier, related to the idea of calibration, the adjustment of calibration and the gain of the photomultiplier tube. The photomultiplier tube must provide consistent output in a consistent manner. It should not vary without any fluctuations. We were discussing the photomultiplier tubes, which, after receiving the light photon that reaches the photocathode, transform it into an electron in a seamless process. Ultimately, this is sent to the preamplifier, which converts it into an appropriate voltage signal in a precise manner. The photomultiplier tube must be capable of handling 3 distinct thresholds in the process of acquiring the incoming light photons or signals to ensure accuracy. This 3 threshold level should not be too low so that if there is significantly high energy from gamma photons, it can convert them into an appropriate electronic signal or volt signal without having issues with its detection efficiency, without compromising efficiency. Regarding the collimator, we talked about 3 aspects in the context of the collimator, if of course the words are moved in our previous discussion. 3 things that we talked about. If you are imaging other components, for example, if you are imaging patients and want to see the kidney, is it better to make your components higher or lower? Should this be anterior or posterior? It is better to keep it stereo. So at that time, you will keep these components. In terms of certain matters for him, or from the perspective of, in this case, it will affect the frequency. The idea is that the more your object size increases, the more you enhance the frequency. Scatter radiation, a secondary radiation that occurs when the primary radiation beam interacts with materials, is associated with the window topic. This interaction is important for understanding radiation behavior in various settings. The window topic acts as a medium for studying scatter radiation, offering insights into its characteristics and effects. This understanding is vital in fields such as medical imaging and radiation safety, where managing and reducing exposure is crucial. The smaller your window is, the better it improves contrast and also enhances resolution. When you increase the window, scattered radiation comes into play, which reduces both resolution and contrast. Of course, if the patient is moving, and this is a stationary patient, the difference in resolution is clear in these two images. One shows motion, and the other shows your patient being still and not moving. Okay, we just talked about contrast, noise, and resolution. You have noise and resolution.